Thank you. Thank you. Yeah, thank you. Thank you so much. So I'm sharing my screen. Uh, do everybody see my screen? Okay, thank you. Thank you so much. Very good afternoon to everyone, the participant and the organizer of this program. I also need to uh, convey my gratitude to Dr. Manoranjan Pahari and Dr. Obiji Suttadhar for inviting me to this wonderful webinar. And actually, this is my first invited talk, so I'm a bit nervous about that. This is okay. I'll try to do my best. Now, as I know, your department is mostly working on mathematics. However, my educational as well as my current research background is quite different. I work on material science. However, there is people who are working on theoretical material science. They use lots of mathematics, but my research focus is mostly based on the applications. So this field will be quite different from your works. Will be quite different from your works. And today, the topic of this talk will be metal-halide perovskites and all around the semiconductor for photovoltaics and optoelectronics. In my PhD and my postdocs also, right now I am working on metal-halide perovskites. Initially, I worked on solar cells. Right now, I am working on LEDs. Now, before going into the details, I first need to show you the outline of this talk. First, I will give a brief description of the semiconductor and their uses in optoelectronics. Next, I will introduce perovskites, their properties, and how perovskites are useful for optoelectronics. And then I will show you some challenges. And finally, I will show the scope of commercialization of this new material. Now, what is semiconductors? As the name suggests, semiconductor sits between insulator and conductors, literally, because their conductivity is higher than insulator but lower than conductors. As you can see in this band diagram, there's an energy band diagram that for insulators, there is a huge gap that is about 5 electron volt between the valence band and the conduction band of the insulator materials. Now, because of this high band gap, we call it band gap, the electrons in the valence band cannot move to the conduction band, and until they move to the conduction band, they cannot carry charges. You know that electrons are the primary carrier of charges in some materials. For that's why the insulators do not conduct charge. While for conductors, the conduction band and the valence band, they merges together. As a result, the electrons are very free to move from valence band to conduction band, and that's why conductors are very much mobile. Like they can conduct much amount of charge. But the problem is, because of this intersection of the conduction band and the valence band, we cannot control their conductivity. That's why they are not suitable for the application that is suitable for semiconductors. Of course, conductors are good for carrying charges, but they are not suitable for this particular type of application that we are interested in. Now, semiconductors has some beautiful properties, like their band gap is not that high like insulators, but not low like conductors. So they have certain band gap about 0.5 electron volt to 4 electron volt. Now, if we can supply sufficient energy to the electrons that are in the valence band, then the electron can move to the conduction band, absorbing that energy. And when the electron moves to the conduction band, they leaves their vacant spaces in the valence band. Now, in semiconductor physics, both electrons and their vacant spaces both can carry charges. It's a bit difficult to understand right at this moment how this vacant position can carry charges, but it's all about theoretical, and it makes our work much easier. That's why we call it as a hole, which are also positively charged. We consider them as a positively charged. Now, both electrons and holes, they are very much important in semiconductor physics, because we develop our ideas based on the behavior of the holes and electrons. Now, silicon is the most prominent and most famous semiconductor. All of you have already heard of it. Silicon is very abundant in our nature because it is collected from the sand. Sand is basically silicon oxide. So sand is very much available in India too. However, as silicon oxide, sand is silicon oxide, getting pure silicon from sand is very difficult, and that requires a multiple stages with high temperature processing, and that's why the technology is very technologically expensive, and they also need very high temperature. That's why we don't have any silicon processing plant in India. So whatever silicon offer, we collect it from China, Japan, or Europe. So that's why silicon is very expensive too. Even though the material is very cheap, the processing is very expensive. That's why the material is very expensive. Another one is the gallium arsenide. This is another very efficient semiconductor. However, the material is very expensive because of the scarcity of gallium in the earth crust. So that's why the gallium arsenide is used mostly for the high value product, mostly in the space programs. And another type of semiconductor which are much flexible about this, that is the group 3-5 semiconductors. If you look at the our periodic table, you will see that at the group 3 and between group 3 and 5, there are these 12 elements which can work as a semiconductor, including silicon and germanium. Now, if you pick up 2 or 3 elements from this group and make a mixture of them, they will work as a very good semiconductor. And by mixing them and also by changing their relative percentage, we can change their different properties, their semiconductor properties. That's why we can use them in different areas, like making transistors, solar cells, or LEDs. Now you see these different colors of the LEDs. That's because of different composition of the semiconductor materials. Because for different colors, we need different band gaps, and that can be achieved by mixing different elements at some certain ratio. That's how we can get different colors from different LEDs. Now, the semiconductors are generally not used in their pure form. They are generally doped with some impurities. Though they are impurities, but they are actually used for good here. Because when we add some p-type impurity like phosphorus, which has one extra electron than silicon, then you can see here that the electron distribution is something different from the silicon. That means we have an extra electron here, and this electron works as a mobile electron. So this material, which we call it p-type material, which will have extra electrons. However, for the other one, if we dope a pure silicon with boron, which has one less electron, you can see here, it has only 3 electrons instead of 4, then we will have a vacant position for electron. That is what we call hole. So these type of semiconductors are called N-type semiconductor, and here hole are the primary conductor of electricity. Now these both P and N-type semiconductor, they make the whole world of semiconductors. Everything you see around us is basically P-N junction. So both P and N-type semiconductor are formed in a single semiconductor material, and they work as, sometimes they are working as transistors, sometimes they are solar cells or LEDs. All of them are basically P-N junctions. Now perovskite is different. What is perovskite? Perovskite is not something new. We know perovskite for more than about 200 years. It was first invented by Gustav Rose at 1879, I think. And the first ever discovered perovskite is calcium titanate. Then they also found barium titanate and some other materials similar to this. And when they analyzed the crystal structure of the material, they saw that all of this type of material contains similar crystal structure, which you can see here. This is the crystal structure of this particular material, and the materials are named after the Russian mineralogist Lev Perovsky. We call this structure perovskite right now. We don't call the material only. Any material that contains this kind of structure are called perovskite. And this is popularly known as AbO3 structure. You can see the A and B2 are metal cations. Here it is calcium and titanium. The A sits in the middle of the room, B is on the sixth corner of the room, you can say, and the oxygen anions, they are occupying these spaces. These red dots are the oxygen. Now, even though oxide perovskites are known for a very long time, they are not much popular because although they somehow they possess some amount of semiconducting properties, they are not that useful when you compare it with silicon or other semiconductors. However, perovskite becomes very popular with the introduction of metal-halide perovskites. Now, what is metal-halide perovskite? This is exactly same as oxide perovskite. We just need to replace the oxygens with halogens like chlorine, bromine, or iodine. And we also have much better options to choose the A site and B site options. Like if we now name this material as AbX3 because X represents halogens, then we have a list of materials that we can choose to put in the A position and the B position. For the B position, the most used materials are the lead as well as tin. Currently, people are using manganese and other metals also. But for the A position, we can choose both organic and inorganic materials like methylammonium, formamidium, or cesium. Now, we can choose any one from each of this segment and mix them together to make a perovskite structure. Of course, we need to follow some certain condition, and it is termed as Goldsmith tolerance factor. Now, this tolerance factor is calculated by using the ionic radius of the A side, B side, and the X side ions. Now, using this tolerance factor calculation, if we get the T value between 0.8 to 1, structurally it is possible to make a perovskite structure. So outside this region, the material will not be a perovskite material. So this is quite a good window to make different perovskite. That's why currently we have about hundreds of perovskite materials with different properties. Now here I have listed some materials. You can see for the A site position, here is 10 different organic and inorganic cations. For the B position, we have lead, tin, and germanium. And for the X position, the choice is much more restricted to iodine, bromine, and chlorine. Now, choosing one from each section, you can make a perovskite, and in this way, we can make about 90 different perovskite out of this simple structure. However, all of them does not possess the similar properties. You can just have a quick look on this graph, and you can say that the material that have more number of red dots is the best one. And considering that, we can say this cesium and methylammonium based perovskites are the best one. And I'm also working on these two particular materials. The methyl ammonium based perovskites are mostly used for solar cells, while cesium based perovskites are mostly used for LEDs. These material, even though all of the perovskite materials possess similar lattice structure, there is some difference. Like most of the materials contains cubic perovskites, some are distorted perovskite. These two are the most common among the different perovskite materials that are used today. And the other structures are not much common. However, recently people are working on ordered perovskite. This material is not exactly perovskite; it's sometimes called double perovskite or something like that. You can see that their chemical notation is quite different from this ABX3. And this material also has some different properties, like they are much more stable than our first one, ABX3. So people are doing much more experiment on these materials. However, they are not as efficient as the first one. Next we come to the optical properties. As we are talking about the optoelectronic materials, so the first and foremost important thing is their optical properties. In the optical properties, the most important part is the band gap, because band gap defines the properties of any material that can be used for optoelectronic applications. Now, there are two, as I've already explained, what is the band gap. Band gap is the gap between the conduction band and the valence band. Now, there are two types of band gaps. One is the direct band gap, another one is the indirect band gap. For the direct band gap, the lowest position of the conduction band and the highest position of the valence band resides in the same location in the momentum space. The x-axis is the momentum space, y-axis is the energy. So these 2 points resides in the same position in the momentum space. That means if one electron wants to return back to the valence band, it just need to release its energy, the energy energy gap between these 2 points, and it can come back to the valence band. So this process is very much efficient. However, for the other one, that is the indirect one, the lowest position of the conduction band and the highest position of the valence band resides at the 2 different positions on the momentum space. That means one electron has to move its energy as well as its position to return back to the valence band, and this process is very inefficient because in this process this is mostly irradiative. Irradiative means when the electron returns back to the valence band, its extra energy is radiated as heat, and heat is something that we don't like for optoelectronics. So this type of materials, indirect materials like silicon, are not used for optoelectronics like LEDs, but they are used for solar cells because solar cells require some different properties. But luckily, perovskites are the direct bandgap materials, so they are perfect for everything, for solar cells, LEDs, projectors, everything. They are very perfect because the electrons return back to the valence band and release its energy as a light. So and that's the primary work principle of an LED. So direct bandgap is the one big property that the perovskite has. Another one is the absorption coefficient. What is absorption coefficient? It's nothing very difficult. Like if you hold a plastic sheet in front of you, you can see anything which is on the other side of the plastic sheet. But if you hold a paper in front of you, you can see. Why you can see? Because the paper has a much higher absorption coefficient, light absorption coefficient. So it absorbs all the light that is coming into it. So this is the main thing about absorption coefficient. Now, as you can see in this figure, I have plotted the absorption coefficient of some different perovskite, some different semiconductor materials with perovskite materials, and x-axis is the energy. It is the energy of the light. You know, the light has some wavelength. So the blue light has shorter wavelength, the red light has a much longer wavelength, and the shorter wavelength means higher amount of energy on the light. So blue light has much higher energy in comparison to the red light. So with different light, with the energy of the light, you can see the MaPbI3, which is a very good perovskite material, has very high absorption coefficient compared to silicon. This is amorphous silicon and crystalline silicon. Also, the gallium arsenide also doesn't have that much amount of absorption coefficient. Now, higher absorption coefficient is very important because if you hold a plain white sheet and a very thick sheet of the same material, in both cases, you will the material has same absorption coefficient, but for the thick sheet, it will absorb more light, even though they have similar absorption coefficient. That means the material with has much higher absorption coefficient, and it can absorb more light in a much smaller thickness of the film. So that's why most of the silicon substrates that are used for solar cells making is about 0.5 millimeter thick, so that it can absorb all the light that are falling onto it. But for perovskite-based solar cells, like methyl ammonium iodide, lead iodide-based solar cells, the film thickness is only about 500 nanometers. That is 1,000 times thinner than silicons. So what is the implication? The implication is that we need much less amount of materials for making a similar quality solar cells. That is an advantage because it will reduce the cost. Another one is that if we can make the solar cell in a thin film, thin films are very flexible and they have several advantages. Like we can coat it on anything, like we can coat it like a paint on the wall. So we can make flexible solar cells. We can also make solar cells on our wall. We just need to paint some materials on the wall and it will work as a solar cell. So that is very interesting. And the third one is the excitonic binding energy. It is a bit technical term. So for solar cells, we need lower excitonic binding energy, and for LEDs, we need higher excitonic binding energy. But for perovskite, and because of their large family, we have different materials that contains both of these properties. So in this way, we have a very large family of perovskite. I have listed some of them here. You can see the change in band gap. This is the band gap value. You can see the band gap is varying from 3.55 electron volt to 1.24 electron volt. So there is a very good range of band gaps among different perovskite materials, and we need different band gaps for different applications. Like for solar cells, the theoretically optimized value for band gap is about 1.5 electron volt, and that is exactly matching with this perovskite. So we can use this material for the most efficient solar cells that can be made theoretically. And for LEDs, we need different colors. And as I have already told you that for different colors, we need different band gaps, because different band gaps means different wavelength of the light. So if we need a red LED, we can choose something like this one, which has about 2.13 electron volt. If we want a green LED, we can choose something like this CSPB-VR3, this emits green. And for blue, we can choose something like CSPB-CL3, around 2.33 electron volt. And in this figure, you can see the beautiful colors from cesium-based perovskite materials with different halogens. You can see Cl, bromine, and iodine. And we can see that all the colors, this from blue to red. Now, these are not LEDs, these are fluorescent dye. That means if we illuminate them with UV light, they will emit their characteristics light. That is blue for this one, green for this one, and red for this one. And we can use the same material to make LEDs, and we will get similar color out of the LEDs. So that's a big advantage for perovskite materials. And here in this film, we can see some perovskite material that are mostly used for solar cells. This is the same material, methyl ammonium lead-based halide perovskite, but we have changed the iodine bromine concentration, and as a result, we have varied their band gap from 2.3 electron volt to 1.5 electron volt. And as the band gap varies, you can see the color is changing from orange to black. Now, if we use these materials to make solar cells, we can make different color solar cells, not only the monotonous black or blue one. We can make orange, red, blue. So that will be very interesting for general perception. So we can color our roof with different colors of the solar cells. And here is another image of different perovskite materials with different band gaps. This spectrum shows the areas of application of different materials, like for solar cells, LEDs, or something, and different kinds of perovskite material also shows different properties, like dimensionality of the perovskite also defines their optical properties. These Metal-Halide Perovskites are available in different forms. The first one, this is the polycrystalline film. So this is basically a thin film. This is a thin film that I casted on a glass substrate. So whatever you are seeing is basically a glass substrate with a very thin perovskite film, the yellow one. And this perovskite film is so thin; it's about 50 nanometers. So it's 1,000 times thinner than human hair. Now you can imagine how thin the film is, and this material can work very good as a LED. So this is the beauty of this material. And the second one, this is the perovskite single crystal. I grown it with cesium lead bromide, and this material is mostly used for making photo detectors. And the third one, this is the perovskite quantum dots. Quantum dots are very tiny particles of the material, and they are called quantum dots because their size is so tiny that the quantum effect starts kicking in their behavior. So their properties, like optical and electrical properties, are quite different from bulk material like this thin film or single crystals. So even with the same material, by tuning their size, we can tune their optical properties. So these are quantum dots. They are actually not much used for making real devices, but people are doing research on this, and they are also very promising. We can also change the dimensionality of the metal-halide perovskite, but here the dimensionality is not like a geometrical dimension like 1D, 2D, or 3D. Here the dimensionality means how many layers of the metal cations are placed between two organic anions. Like, this is the layer of a metal cation, ABX3. This is the B layer. So this is the layer of the B, and between there only one B side cation is placed, and then there is the organic cation, and then again one layer of the metal cations. So that's why we call it n equal to 1. This is the one-dimensional perovskite. This is the n equal to 2. That is a two-dimensional perovskite because we have two layers of the metal cation placed one after each other, and these layers are separated by the organic cations. And this is the 3D perovskite. We call it n equal to infinite because infinite number of metal cations are placed one after each other. So this is what we call 3D. And by tuning their dimensionality, we can also tune their optical properties. And as we go towards the lower dimensional perovskite, their stability generally increases. So we are now using both lower dimensional along with the high dimensional materials together to get both very good performance as well as very good stability. Now, another thing is the defect tolerance. Now, we see in the crystal structure that all the lattice points are placed in a very organized way, but in real life that doesn't happen. This is the ACM, that is the scanning electron microscopy image of a perovskite film that I casted on glass. You can see there are different segments of different thickness and sizes. That means there is a boundary between two different grains. We call it grains, and there is a boundary between two grains. And this boundary region, the lattice structure is distorted. That means the continuity of the lattice structure is not available at that point. And these points are working as a potholes on the road. Like if you want to drive a car and there is some bumper, then we have to stop, or we have to reduce our speed. So this gain boundary works similar in our materials. Like they work as a boundary. So the charged carrier like electron and holes, when they go to this boundary region, they either slows down or they just return back to the other side by getting deflected by these boundaries. So that's a big problem for polycrystalline films. Now they also work as a radiative recombination center. What is that? That means if there is some boundary, then the electrons or holes will get accumulated at this region, and they will be trapped in the boundary region. So they are not now available for our other optical and electrical mechanisms. So these electron ion holes are not available. That means they are working as a point of sink. So they are sinking these charged carriers. So this is not desirable for good materials, good semiconductor materials. But interestingly, these perovskite materials are very much tolerant about these defects. Like even though there is a very high density of defects, they still works. And why they works, it is still debatable because people are working on this, but there is no concrete answer for this reason. But these perovskites are working, so that's interesting. And the last point is the low material cost. These perovskite materials are found in normal chemical laboratory. So these are not very expensive, and their fabrication process is also very easy. Like we can just spin them or deep coating, all these solution based process technique, and these are very common technique and it's available in almost every lab. So we can make perovskite films just by using these techniques, and that's why the device processing technique as well as the material cost is very low. uh, that's why the whole process is much cheaper than our silicon based or the other gallium arsenide based perovskite based solar cells or LEDs, and this whole process is done below 200 degrees centigrade. So that is also a very good thing, because the energy consumption for making a solar cell will be much lesser if we use perovskites. Now we go to the incredible journey of perovskite in the field of optoelectronics. The perovskite materials possesses so much different properties that we can use it for solar cells, LEDs, laser photoreactors, and other things like supercapacitors and piezoelectric energy harvesters. But those two are out of the scope of this talk right now. So I will mainly focus on solar cells and LEDs. Lasers and photoreactors are not that much developed right now. So I will just give a small information on that, but I will mostly focus on solar cells and LEDs. Now, these perovskite materials, because of their very good properties, they are so popular right now, and different labs are working on this, that we get about 4,000 number of articles published per year. So now you can imagine how popular this material right now among the material researcher. Now, let's go to the solar cell. Why solar cell is very important? Because as we all know that we are running out of fossil fuels. So in that, that's why everyone, the government tries to implement more solar photovoltaics so that we can harness the energy of the sun to make electricity and use it. But currently there are different problems, like the silicon-based solar cells, though they are much cheaper than earlier, but still they are very expensive. And the other thing like hydropower, nuclear, they have also their own demerits. So solar can be a very good solution if we can make them available to the common people, so that they can use it on their roof. And the total roof area of a country is very high. So if someone uses solar panels on his 10 by 10 room, it is enough to produce enough energy to run all the electrical appliances that he's using. So this is the total amount of solar energy available to Earth, and this is our global power demand. So you can see that is almost nothing compared to the available energy on Earth. And this is the total number of PV. This is the total amount of PV installed right now. I have exaggerated this because otherwise it will be so tiny to see. So there is huge potential that we can harness the sun and meet our global power demands. But for that we need to reduce the cost of solar cells, and that is one big point. And here perovskite can be very promising. Now, solar cells are, as I've already told you, that solar cells are basically PN junctions. So the P type has more holes and the N type has more electrons, but they don't go to make the circuit complete, because they need energy. How the energy is coming from? It is coming from the sun. The sun is providing the energy in terms of light. That light is pushing the electrons and holes in their own different ways to complete the circuit, and that's why we get electricity. And this is the silicon solar panels. You have already seen this many places. The most important parameter of a solar cell is the efficiency. What is efficiency? Efficiency is the how much amount of electrical power we can harness from unit optical power. Optical power is the sunlight. That's the optical power. We can sense the power of the sunlight when you go out in the sun. You can feel warm. That's the power coming from the sun to you. So the solar cell is also using that same power to make it into electricity. Currently, the consumer level silicon solar cells, they provide about 17% to 20% conversion efficiency. That means if you put a solar panel and it gets about 1000 watt per meter square of sunlight, then it will produce about 200 watts of electrical power. That is not small, that is quite good. And if we move to the perovskite solar cells, it has different advantages. First one is the structure. This is the structure of a perovskite solar cell. There are 5 different layers, and all the layers, the total thickness of all the layers is less than 1 micrometer. 1 micrometer is about 50 times thinner than a human hair. So now you can assume the thickness of the layer. But the advantage is that all the layers can be deposited in a solution process technique, and that technique is very cheap. So the perovskite solar cells can be made with a very low cost instrument and at much lower prices than silicon solar cells. This is the real photograph of a silicon of a perovskite solar cells. This golden color as the gold electrodes on the back electrodes, and this bluish reddish color as the perovskite layer. This is the cross-sectional scanning electron microscope image of a solar cell, perovskite solar cell. This 1 micrometer, the total thickness of this thing is 1 micrometer. So now you can assume how the different layers are placed in such a compact form. Still, this material work very good as a solar cells, and using that technique we can make different type of solar cell, like this flexible one. This is a standard solid one, and this one is a patterned one. Now this material, even though they are in a thin film form, they are so efficient that only in 12 years the perovskite solar cells has shown efficiency up to 25.5%. This is the perovskite solar cells, and the progress of perovskite solar cells efficiency in the last 12 years. We have reached 25.5%, while the silicon solar cells took more than 50 years to reach only 23.3%. So now you can imagine how promising this material is. And this is another one, that is the concentrated perovskite solar cell, which shows about 30% efficiency. But this is not very much usable for common people. In this table, I have compared the different properties of 3 different photovoltaic technology. First one is the cadmium tellurium, is CDTE, and silicon and perovskite. You can see that the perovskite possesses green mark on most of the criteria, like the material cost, fabrication cost, energy payback period, the efficiency, abundance, and LOC. LOC is the localized cost of electricity. So we see most green lines in the perovskite column. That means the perovskite is the best one among all 3. However, it has a red thing, that is the toxicity, because this perovskite material contains lead, and this lead is very much toxic. I will discuss more about this later. So far, based on these parameters, perovskite materials are much better than silicon and cadmium tellurium. Now let's move to the light emitting diodes. Now when you see light emitting diodes, we generally think of some fancy lighting in the Diwali, or some lighting on the back of auto. But LEDs are much more than that. First one is the lighting, that is one use. Second one is the display technology. Right now, all of you have already heard of the word OLED, organic LED. Many smartphones are right now using OLEDs, and OLEDs have much better color quality than the traditional LCD displays. So this is for the benefits of LEDs, because LEDs are much more color accurate than the LCD technology. And the third one is the communication. Like the fiber optic communication, it is totally based on LEDs. In fiber optical cable, there is no current, only the light. The light is carrying your information, and that light is generated from an LED. So that's why light emitting diodes are very much important. And the basic structure of a light emitting diode, or LED, is just similar to solar cells. It's the PN junction diode. However, the actual architecture is much more complicated. You can see the actual architecture. There is more than 10 different layers to make a LED work. So the process is quite very difficult. And the LEDs is so important right now, mostly for the lighting. The blue LED changed the world, because they have reduced the total cost of electricity used for lighting after the introduction of white LEDs. And white LEDs are based on blue LEDs, and that's why blue LEDs are so important that Professor Akasaku, Amano, and Nakamura got Nobel Prize in Physics in 2014. So that's the importance of LEDs right now. And there are different figures of merit of a LED. The key parameters are the luminance, which you can say is the brightness of a LED. Second one is the quantum efficiency. That means how efficient the LED is, which in common man's word, how much electricity it can save. And the third one is the correlated color temperature. It is more important for the display technology. How color accurate the display will be, it depends on the correlated color temperature or the CCT. I will explain it later in details. And the third one is the switching speed. It is mostly important for communication. Now let's go to the color accuracy. And there is a term called color gamut. What is color gamut? Color gamut is something, if you see the monitor of your screen with a microscope, you will see like this. The monitor is not some uniform thing. It contains small pixels of red, green, and blue dots, and they make the screen. And the processor controls the brightness of these different dots, the red, green, and blue, to make different colors, and finally make the images on your display. In OLED display, these dots are actually tiny LEDs. So the LEDs are turned on and off to make the different colors. And that's why the OLED displays are much more power efficient than the LCD displays. But right now, PLEDs or the perovskite LEDs, they are showing very good potential in this display technology. Because if you look at this image, this is the color gamut. If you look at this image, you see that the right part is the red, and the top part is the green, and this bottom left corner is the blue part. So this is the total amount of colors that human eye can see. Now, different display technology has different red, green, and blue value, and the area contained by these 3 points is the number of different colors that it can reproduce. For the LCD display, you see this triangle area is very small, but and this one is the NTSC standard, the red one, and the black one is the color gamut that can be produced by perovskite LEDs. So this is the largest among all of these. So if perovskite LEDs comes into the market, it will be the most color accurate LEDs, even more than the OLEDs. Because if you see here that the OLED spectrum of LG TV, you can see the blue dot, green dot, and the red dot, they are actually getting superimposed with each other in this region. So this is not actually good. So they should be distinct along the wavelength axis. But for perovskites, their emission peak is so thin that they generally do not make superposition. That's why their color is so much accurate. And that's why perovskite LEDs are so much promising. Now, this is the structure of a perovskite LED. Unlike the other one that I have already showed you 2 slides ago, these perovskite LEDs has much less number of layers. It has only 6 layers. So it is much easier to fabricate, and also we can also use solution-based technique to make the LEDs. And in this technique, right now I'm also making LEDs. These 2 LEDs are made in my lab last week. And there are different colors available. This is the blue one. This is the not exactly green. It is greenish. This is the red one. And red, green, and blue. We need all 3 of these colors to make a display. So right now we are working on this, and we are getting very promising result. However, there are some challenges. We need to meet them before we can make it easy for the commercialization. And other field of application of MHPs are the photodetectors and lasers. Photodetectors are very important for communications, because the LED produces the light that carries your information through the fiber optic cable. But what receives that? In the recipient end, we have a photodetector that receives the light and converts into electrical signal. Now, photodetectors, the conventional photodetectors are color blind, so they cannot detect different colors. And color, the selectivity of colors is somewhat important, like in camera sensor or something, where in this type of applications, we need the color sensitivity. So for that, people generally use a filter to make the different photodetectors to see only some different colors. But for perovskite, due to their very good optical properties, we can use the perovskite crystal itself without using any filters. We can directly use the perovskite crystal, because they have different band gaps, and different band gaps mean they have different regions of interest in the wavelength spectrum. You can see here that 3 different perovskite crystals are stacked one upon another. First one is the methyl ammonium lead chloride, then the bromide, and then the iodide. And due to their difference in band gap, The first one detects light only in the blue region. The second one detects only the green light, and third one detects on the red light. So these three perovskite photodetector pixel, they can detect all red, green, and blue light, and can make a very good camera sensor. And another one is the perovskite laser. However, this is not yet very developed. So people are trying to make a good laser out of this. So I'm not going into details of this thing. And what about the challenges? So far, I have told that perovskite materials are very good and it can replace anything that's available in the earth, but they are still not available in the market. Why is that? Because the first problem is the stability. These perovskite materials are very unstable compared to the other semiconductors, and they are very unstable in presence of light illumination, in moisture, in electrical bias, and several other things. And their stability is so low that they can be as short as 1 minute to few hours. So that's why this material at its current form are not promising to apply in commercial products. But people are working on this, and so far the maximum stability that we have got with perovskite solar cells is about 1,000 hours. So it is increasing day by day. So maybe in few years we will see them ready for the commercialization. And another one is the toxicity. Most of this perovskite material contains lead, and lead, we know, it is very much toxic, and it is very much toxic to us and also the other environmental things. So we cannot use lead without certification from the pollution control board. That's why perovskite material has some problem before getting launched for commercial products. However, there are other ways to replace the leads, as well as enclosing the device in a such a way that the lead cannot go out of the device. So this is possible, and research are going on. But even though of these two different problems, we have several opportunities, especially for India, because currently, as I have already told, that silicon-based solar cells or the electronics is not developed in India because their purification process as well as their fabrication process is very expensive, and they require a very high amount of research and development stages. So this is not produced in India. We mostly procure them from China, Japan, or Germany. But for perovskites, it is so easy to make, and it is very inexpensive that it's very possible to make the perovskite solar cell here in India. Actually, in India, very different labs are already working on this, and they are also having a very good progress. So that is very important for developing countries like India. And another thing is that because of their low material cost as well as low fabrication technique, low cost fabrication technique, these perovskite materials will have much lower price per watt in comparison to crystalline silicon. You can see for crystalline silicon, the price of the solar cells per watt is about $0.7 per watt. But for perovskite, it will be around $0.4 per watt. So there is a huge improvement, and this is our anticipated costing. So if the big company starts to make the make perovskite solar cells, then the cost even will be even lower. So there is a very good opportunities for perovskite solar cell and LEDs. And here is the current state of commercialization. Different companies have already started working on this. These two are two startups. The Oxford PV is UK-based startup. They are already working on perovskite solar cells, and they have demonstrated that by 2025 they will show their first commercial product of the perovskite silicon tandem solar cells. And the second one is a Swift Solar. This is a US-based company. They are also working on perovskite solar cells and LEDs. But in India too, we have one company called P3C. They are working very well with perovskite solar cells. So maybe with the other companies from abroad, we'll also see our made in India solar cells in near future. And among Indian research community, perovskite material is very much popular and many Indian researchers also working on this thing. If you search for perovskite papers, most likely you will see some Indian name on the papers. So people are working in India and in abroad to a very high extent on perovskite things. So maybe we will have very good potential for perovskite commercialization in India. So this is what I had for this talk. Now, thank you everyone for your attention. Thank you very much. I think the field is quite different from yours, so maybe that's a point of difficulty for others also. So far, I have worked on a different kind of thing. The first one is by introducing the 2D perovskites. As I have told you that 2D perovskites are much more stable than the 3D one. However, there is a problem that the 2D perovskites are not much promising for their optoelectronic properties. That's why if we want to use only 2D perovskite, that won't be a good option. But we can mix 2D perovskite with 3D perovskite, so that we can make use of the stability property of the 2D perovskite as well as the performance of the 3D perovskite, and that's how we can improve both performance and stability. That is one point. Another point is that we can dope the perovskite layer with different metals like zinc or some other lanthanides to increase their stability. So that is the second way. The third way is that we can improve the encapsulation. Like currently people are using different kinds of polymers like PMMA to encapsulate them from the atmosphere and other properties. So that is the third way. Yeah. Yes. Unfortunately, please. Yeah, unfortunately, India doesn't have a big reservoir of all these kinds of different semiconductor materials. Only we have silicon because we are we have sands. But the processing technique is very difficult and it's also very expensive. So that's why even today we don't have a single silicon purification plant. But for this perovskite and similar other materials, which are much easier to form and they are very cheap. So IC promises that we can use our own chemical industry to produce this kind of semiconductors, and later maybe after 10 years or 15 years, we'll make our own semiconductor devices out of the materials that are developed in India. Yes. Yes. Mhm. Mhm. Yes, the crisis is not because of the availability of silicon, because silicon is very much available. The crisis is mainly because of the processing. And during the COVID time, due to the lockdown, many factories had some restrictions, so the production was limited. That's why we have got the limited production of silicon. That's why everything related to semiconductor was got suppressed from making chips or everything like that. But of course, if something like that happens again, it will happen one more time. But as I have already told you, that these kind of new semiconductors, they are not that difficult to process. So the processing technique is much more easier. So it will be less hampered by this kind of problems. So that's a promising thing about this thing, about this semiconductor. Mhm. Mhm. Currently, silicon is the best one because it's most available. Of course, making is not very easy, but it's the most available. That's why every solar cells you see around here, it's mostly silicon-based solar cells. There are some CDT-based solar cells also, but only 5% or 10%. So if you at this current position, the cost for solar cells is lowest for silicon one. But there are some solar cells for with gallium arsenide, but they are very costly. They are much more efficient, but they are very costly. So we can say the silicon is the best one right now. Thank you. Thank you. Thank you. Thank you too. Thank you, beyond us. Thank